At first glance, the many rocket planes that flew over Rogers Dry Lake between 1946 and 1975 seem an odd assortment. From the bullet-like XS-1 to the wingless flatiron-shaped X-24B, each was a pioneer of its time with form closely following function. But beyond the multitude of aviation firsts these aircrafts achieved, all shared one common purpose. They were flying laboratories, built and flown in the pursuit of aeronautical knowledge. Their story begins with the pioneering work carried out by Austrian physicist Ernst Mach in the late 19th century, which first revealed the detailed relationship between projectiles moving at high speed and the fluid, in this case air, through which they were traveling. As an object moves through air, it generates a series of pressure waves that radiate away in all directions at the speed of sound. If the object is moving at a subsonic speed, where none of the airflow around it exceeds the speed of sound, then pressure waves radiating ahead of it will inform air molecules in the object's path of its imminent arrival, allowing them to move smoothly out of the way. Consequently, the air does not become compressed by the object. However, as the object accelerates, the distance between it and the pressure waves radiating ahead of it is reduced, allowing air molecules less opportunity to move away from the object's path. As the object approaches the speed of sound, the pressure waves and air molecules ahead are unable to move from the object's path before it arrives, and consequently, they become compressed into a shock wave. For many years, scientists had known that projectiles could move faster than the speed of sound, but using the recently developed technique of Schlieren photography, Mach was able to record the previously invisible patterns of shock waves generated by fast-moving projectiles in detail for the first time. The speed of sound itself is not a constant value. Rather, it varies with the temperature and pressure of air. Within our atmosphere, the local speed of sound generally decreases as altitude increases. For example, at sea level, under average conditions, the local speed of sound is in the region of 760 miles per hour, but at an altitude of 35,000 feet, where both air pressure and temperature are considerably lower, this decreases to approximately 660 miles per hour. In honor of his groundbreaking contributions to the field, the ratio of an object's speed with regard to the local speed of sound is known as its Mach number. Unusually, for a unit of measurement, Mach appears before a value rather than after it. Mach 1 is achieved when airflow over the entire object exceeds the speed of sound, at which point the object is said to be supersonic. While aerodynamicists recognized that simple symmetrical shapes like bullets could readily exceed Mach 1, the prospect seemed less certain for more complex objects, such as an aircraft. In the wake of the First World War, improvements in aerodynamics and propulsion led to a steady increase in the speed and altitude at which aircraft could fly. But although piston engines were becoming increasingly powerful and therefore capable of turning propellers at higher speeds, the propellers themselves were not generating the expected increases in thrust. Puzzled by this apparent shortfall, aerodynamicists, including Dr. Hugh Dryden at the U.S. Bureau of Standards, began to investigate the problem. As propellers spin, their outer sections travel farther than their inner sections and therefore move at higher speeds. A propeller's airfoil generates lift, and therefore thrust, by forcing air to flow faster over its upper surface than its lower surface, just like an aircraft wing. But as propellers began to spin faster, airflow over the outer sections of the blades was now exceeding 600 miles per hour, a high percentage of the speed of sound.